support for alles geweest op de netwerk zijn dan denk sowieso. Ja, ik wil zeggen dat je zoiets deed of zo. Oké, weet ik niet. Maar ik kan niet graag iemand in het systeem zijn. Ja, dat maar we moeten het niet doen. Precies al van de referentie van de
Cool. Yes, seems to be working. Dankjewel.
Ik wil denken dat je kunt zo ik weet niet, ik heb het niet gelezen. Ik heb bijvoorbeeld gisteren een slice gekomen. Ja, dus inderdaad, de worden
Right. Good afternoon, everybody. I'm Tim. I'm a web performance architect at Akamai, and in this short session, I will cover QUIC at Akamai, and I will do it from two perspectives. So Akamai is a CDN, and we already heard the name already a few times today, and I will look at, we are two big types of content we serve is video content. So we will look at some real life numbers of QUIC at Akamai for video. And then the second part is more web performance related content. And that's what I'll do basically. And feel free, of course, to ask any questions. So media streaming, I'll straight away dive into the results. So at Akamai, some of our media streaming customers, they have the option to opt in for QUIC. Whenever I talk about QUIC, it's GQuick. So of course, Akamai will at a certain point in time support the ITF version, but at this point in time, every night I talk about QUIC, or the numbers here are GQuick. And this is a live streaming event, live sporting streaming event last year, somewhere in the summer. And this is 42 million data points. So not like a small test, not under lab conditions, real conditions for a live streaming event. And what you see here on the graph is the blue bar shows the throughput, so amount of megabits per second for TCP. And then the orange one shows the same throughput for QUIC. And what you can see is that across all, let's say, across the whole performance distribution, we actually see that QUIC performs better than TCP. If you look at the median, and that's like nicely in the middle, it goes from 10 megabits per second towards 12.5 megabits per second. So that's 25% additional throughput. Now, why do our customers care? If you do live streaming video, the bigger throughput you have, the better quality you have, but also the lower the chance that that you get some buffering. So no, I have numbers, but I'm not able to share them. But in general, it's customers on QUIC. They show less, they had less buffering, and also they had a better quality video. You have a question?
Yes, what condition control did you use? Yes,
I have no clue. I have no clue. So this is real time. So it's there. You also see QUIC AA. That's like an internal. That's an internal mode. Let's say with our settings at that point in time. But I'm not an engineer working on this one. This is, let's say, more me sharing this data. So at Akamai, from a congestion control perspective, we support BBR, we support also the others, but we don't enable BBR out of, let's say, for everybody just because it's cool. It's basically depending on the network conditions and the type of network talking to us, we might apply different settings. So if this is like, I don't know, sorry.
And one quick question, so the throughput is a network throughput, right? Not like the actual cable we see in the application.
This network throughput, yes, correct. Yeah, so BBR is, so we also support BBR for TCP.
Okay.
Yes, but depending on the time of the day, the network talking to us, we might fall back to an older protocol automatically. So I think if you look at the amount at the live data set, there are other events. We have similar things for on-demand streaming, etc., and all share that same pattern that QUIC shows a bigger throughput. Since I think that was on one of the slides, it was mentioned that Akamai now has QUIC support in technical preview since October. So in Akamai, you have two divisions. You have the streaming division and more the web performance division. So that's like the technical preview is indeed since October 2018 for the web content. And basically, I'll just show live data from there. Let me go back to the...
Sorry, can I ask one?
Yeah, sure. Sure.
On the previous graph, I would think that like you have much less QUIC clients than you have TCP clients, right? Because QUIC is only on.
Yes. So what we did there is we actually this only shows QUIC enabled clients, and there 50% of the QUIC enabled clients we did TCP, and of the QUIC enabled clients we also did 50% VDR. So it's not exactly 50%, but it's roughly the same.
So you tried on 50% of the clients you tried to use QUIC, but it could also fall back to TCP.
Yes. So let me go to the demo. So the first thing is on how to enable QUIC on an Akamai property. An Akamai property is basically where you can set up TTL, etc. So for beta customers who opt in, they just have a default feature called QUIC. It says now today that it's GQuick, and you can enable it up to 50% of the traffic. Why not 100%? In the end, we also care about the stability of our platform, and as it's technical preview, the last thing we want to do is that one customer setting 100% to QUIC while it's technical preview, and that we break other customers. That's the reason why there is like a certain limit. We also want to use that live data to validate how our platform behaves under, let's say, real-time conditions. So that's the reason. Another setting, oops, I'm confused with that.
Can you share how many people enable that and what they set as a percentage?
I will show that straight away. Most of them, they go to the full 50%. There's another thing like where, so you can have also the certificate settings. So there you can see that this is an SNI certificate, and you can then decide at the certificate level if you enable QUIC or not. So those are the two things.
The font size a little bit?
Yeah, sure.
So for the stream.
Sure, let me zoom in. Is this better?
Yeah, thanks.
Yeah, you're welcome. So that's the only thing you need to do to enable QUIC. So I did this on my website. So the positive thing is I run the largest scale modeling website in the world. The topic is not relevant, but the advantage is it's my personal website. It's on Akamai, and it gets 4 million visitors a month. Why is this nice? Because it's like enough traffic to do some, let's say, some nice testing. It's not the same as a blog post, let's say your personal blog, where the only one you are, let's say, refreshing content. So what you see here is I enabled QUIC, and in theory, 50%, if you go visit the website, in theory, you can see in 50% of the cases that QUIC is enabled. So that's what I did. Now, what are the benefits from it? I also have real user monitoring, so let's go straight away in there. I inject a little JavaScript, and it's based, this is now the commercial one, but it's called Boomerang. So I don't know if you heard about Boomerang. Boomerang is an open source, real user monitoring solution. So it's a little JavaScript snippet you embed on your page, and that will read the browser navigation timing API, resource timing API, so the same as you see in a waterfall, and then can send that to your backend. In this case, it's Mbox. So what you see here is, this is now live, the website data on my website. So going to the QUIC part. Now, the advantage, doing synthetic tests or in the lab conditions has some advantages because you always do the same pattern. It's always the same, let's say packet loss X, latency Y, and it's always under the same conditions. Advantage with real user monitoring is that you get everything. Like if I'm at home and I visit my website on the Wi-Fi connection at the bottom, or if I'm going upstairs, it's already a different behavior. So this is really the wild. That means you also need to be careful that you don't make wrong conclusions. So what you see here at the top is there is only 2% of QUIC. So this is only 2% of QUIC enabled. Another reason is, although I set it to 50%, is Akamai now has a protection mechanism. If there is too much traffic on a certain server, then we disable QUIC automatically. So if there's like a large load suddenly coming in on a web server, we basically go for the full protection and fall back to scalability we know. So that's the reason why this is a bit lower.
Is it to protect the network or to protect the server load?
Yeah, it's protect that server load, which is part of the huge, let's say, which is part of the network. So it's just to make sure that our global network, our global performance of customers not enable QUIC can't be impacted by one website which has enabled QUIC. So now this is now set to, let's say this is now at a low barrier. In theory, the symposium is coming 1 week or 1 month too early. We are now gradually making this, let's say, now that the baseline is set, we will gradually increase these levels. So I hope in 1 month that this 2% will go to 10%, 20% to have better numbers.
But I guess sorry.
Go ahead.
You did some benchmark testing just for your QUIC implementation, right? Just knowing like how much memory.
Yeah, sure, of course, but I don't have these results. Okay. I'm not part of that team. I'm more like on the, let's say, the team talking to the customers.
So is it? So I guess it sounds more. It's not a real concern. It's just like trying to do it very slowly.
Yes, just to be sure. Yes. In theory, you can just like remove that filter and see what happens, but yeah, we can't take that risk.
But the reason that you limit the QUIC traffic is simply because of the resources that QUIC itself takes, or?
Yeah, it's a variety of reasons. We just want to make sure that that nothing in that new protocol can harm the platform in any way. That can be from a security perspective, can be from a performance perspective, can be, let's say, all the unknowns. So therefore, we start slow to make sure that, yeah, we don't go too fast.
Yeah.
So the next thing I want to do is like, can I see some performance benefits of QUIC versus versus TCP in the wild on my own website? So I know 2% data is not ideal. I double checked that, but it was still, let's say, Roman still said it's worth sharing this data. So what you see here is over time. So the little purple box is, say, the H2 traffic, the HTTP QUIC traffic, and at the bottom you see the performance. So ignore the QUIC version 44. That's just 8 data samples. But if you look at the timings, the TCP connection time. So the TCP connection contains SSL handshake as well. So there you already see a small improvement. On first contentful paint on my website, you don't see an improvement, and the reason is I have plenty of other optimizations with critical CSS, etc. So that first paint happens before actually the benefits of QUIC really start to get in. So that's for my website. That's another thing. But if you look at, for example, the main JavaScript or the logo, you can quickly see that QUIC starts to outperform the standard TCP or H2 part. Now, as I'm looking in the wild, there at the top, you see that I only selected Chrome 72, 73. So we are only looking at newer browsers who support QUIC. So we don't have, let's say, performance differences of an old browser which is not as optimized as Chrome. So we zoom in only on the QUIC enabled browsers. Now, this is for the median. If you look at, I took the 80th percentile there. So these are the slowest 20%. And there you see a similar thing that for the main.js, the logo and the hero images, that these resources are served faster. And also here you see the performance distribution that in general QUIC outperforms H2. just having a look at the current browser. So these are the browsers I see on my website, which have QUIC enabled. And at the bottom, you see all the browsers for that. And another one is like just good luck, bad luck. Especially as we are looking at a very small sample set, just having a few users with a good connection might, let's say, interrupt the things. So what you see here is the performance distribution. The top shows for that JavaScript file, the resource timing for downloading a JavaScript on H2, while the bottom one shows QUIC. And although there are some fluctuations up and down, in general, I think you can say that QUIC downloads the JavaScript faster than compared to H2. So even with, let's say, as sample set is rather low, even if you add some margins, I think the results are as expected. And then this was another thing. This was just to validate the amount of data sets, and here my website had an issue, so that's not related. So that's the data. Any questions? Is it as expected based on what you saw before?
What would you say are the reasons that QUIC is faster now? So can you conclude anything? I mean, is it only the handshake, for example, that makes it better?
No, because the main JavaScript there, the handshake is already, so my main, maybe a good one that you said, so my JavaScript sits on the same domain as on the www domain, so you don't have that additional overhead of DNS, TCP connection, etc. So main JavaScript is already after the handshake, so that can't be it. So this is, this is in theory it. I have no, yeah.
But you don't know whether or not TCP and QUIC are configured similarly. Because it's basically what Akamai.
Yeah, this is now, let's say, in the wild, a live website yes. On Akamai. So this is not a test property. This is, let's say, Akamai in real time on a real time website under real world conditions.
So how did you? Because that's HTTP2, you said, right?
Yes.
Maybe you know better than I, but I thought like in HTTP2 is it that every request is sent on a separate stream, or like how does the mapping work?
So
Yeah, there was also that where you said like all headers on a different stream at the table. I'm not sure what HTTP2 is doing.
It's very similar to H3.
No, it's not. Actually, there's no H3 continuous, right? Instead, it's nothing.
No, it's similar to how H3 is currently doing it. Then there are separate streams for individual resources. You just have the headers and the response body in the same stream.
Okay.
The mapping is the same. It's more or less the same. If that answers.
But I guess it's one of the big reasons that you actually have streaming and no header line.
Yes. Yeah, and the only potential downside I think in this real-time data is that, let's say, an underperforming region, let's say further away, doesn't have any QUIC enablement and therefore skews the data. So that's the only chance I see that I didn't zoom in on the right, that I'm not comparing apples to oranges or apples to apples. But based on my data, it should be fine. And I hope that in a few weeks, when the amount of samples goes up, that it gives a more stable and more usable data set. But I wanted to already share this with you.
Did you also show the total page load time?
The total page load time is, it's not in here. If you want to see it, let me quickly modify it. You want the load time, something else? So, live demo. So now it's basically every single resource, every single request, XHR requests are basically tracked. And then, so now we're looking at the load time. Where is it? load time one, but yeah, now, why don't I look at the load time? Because this website also has advertising, and the ad request can really skew the load time, especially, this is also, yeah, for example, a search page is much different than a home page, much more content, less content, and especially as we are now looking at a small subset, yeah, load time, although they are very similar, I think it's basically, let's say, good luck or bad luck, let's say.
And you know, you can play around it nicely. Can you maybe also, is it possible to only show the data for the mobile versions of Chrome?
Yes, sure. So, mobile devices or mobile versions of Chrome?
I mean, devices.
Devices. So let's see if I have, let me add a filter. If I'm over time, it's not now my fault. Let me go to edit mode. Let me add a filter. So we want to look at device type. Device type. And we want to look at model. Apply. And did you actually, now we're looking at mobile device, but did you want to see did you want to see cellular connection? Because mobile device. But because in the end, your mobile device can still be at home and your Wi-Fi, then it corresponds to cable. So let's first look at mobile device.
Stop showing off, Tim. It's clear. Wi-Fi is amazing.
Yeah, so that's the mobile device. So I think very, let's say, similar results is that in general, the assets are loaded faster. You want to see the cellular connection, or I can? Yes, let me actually check that.
How do you know that's a cellular connection?
There are a few things actually. So you have the cellular connection. In the new browser APIs, you can actually extract if it's like 2G, 3G, 4G. So it's basically the browser tells you what the connection is, and this connection type is now based on Akamai knows which network is talking to the server. So we know, hey, it's a mobile network or it's a broadband network, and based on the IP of the end user, we know from which network it comes. And so that's how we do the classification. And here you then see the, let's look at the data. So this is cellular on mobile phones, and also there you in general see that it's faster.
Okay, thank you. It's a really nice tool.
Cool, perfect. Any additional questions? Yes, Owen?
I just want to say I'm very happy to see this data because it's contradicting a lot of things that we saw before. Like here you say the initial handshake doesn't really matter that much. You mainly see the speed up from later in the connection due to the non-identified blocking. It's also interesting that it's a site that loads extremely fast.
Yes.
Like by today's standards, and still you were able to have a very big impact.
Yes.
And I don't really care at this point what the reason is. Because for your users, they won't care.
They don't care.
Just enable it, they will see the difference with TCP and they will be, okay, QUIC.
Yes.
QUIC is the one thing to go, and that's going to do more for QUIC adoption.
Yes. Now there is one thing, and it's actually good. You don't see the benefit on the TCP connection, and right now we have an alt SVC. So basically, how long to expose that this browser is QUIC enabled of only 1 hour. Like in the future, this will increase. The reason there is if we for some reason need to disable QUIC, that we impact users with the least amount of time. That means that's also the reason why some of the let's say these connections are not, let's say you don't see the full benefit, because an end user coming in multiple times a day on my website will, let's say, has to restart all over, let's say everything all over again instead of straight away going to let's say going into QUIC mode. So that will improve in theory in the future as well.
So the numbers we're looking at is when you,
Can you,
this is the time between you send out the request and you get the full reply, or what is actually, how do you measure those times?
This is, so the delay, if you now visit the website, in 3 to 4 seconds, you see the live data.
No, I mean like for example, the main JavaScript, like what is actually the time frame you're measuring?
Okay, in this case, the main JavaScript is the request start, so the time that the browser actually requests the JavaScript till the response ends. So we're looking at the response. So it's the resource timing API, request start, response end. Thank you. Thank you very much.
Thank you.
So hello, my name is François, and I will talk about adding a forward error correction extension to the QUIC protocol. So before we start explaining what we did, let's just have a quick reminder of what is forward error correction. So the basic idea of forward error correction, I will say FEC to be more short, is to send redundant data along with our important data. So the redundant data, we'll call it repair symbols, because they will be used to repair the important data that we lost. So the redundancy is the repair symbols, and the important data is the source symbols. So it's interesting because it can allow us to recover from the loss of some data without the need to wait for a retransmission. So if we send the repair symbols just after the source symbols, if we lose some source symbols, we will be able to recover it immediately. So it can be useful, for example, in short transfers, like short request responses, but also in real-time communications where we cannot afford to wait for a transmission like video conferencing, etc., when we want to keep really small buffers. One of the well-known drawbacks of FEC is that it often requires some additional bandwidth. Because as you don't know which packet will be lost, if no packet is lost, basically you have sent redundancy for nothing. So that's one of the common drawbacks of the approach, but it's not always the case. So let's take a look at a small example to be sure that we completely understood. So here we want to send 8 data units, 8 source symbols. It could be QUIC packets, but it could also be QUIC stream chunks, for example. So we are here, we just consider that it's data units, and we want to send 8 of them. So we'll separate them in 2 blocks of 4 units. And for each block, we output 2 repair symbols. So here we output R0 and R1. And here we output R2 and R3 for the second block. And what we send at the end is that. So we send the first block, then the 2 repair symbols, and then the second block, and then the 2 repair symbols. And so if we have the case of some packet losses, for example, let's say that we lost D1 and D2, we are now able to recover D1 and D2 because we received R0 and R1. And we are able to recover from the loss of D7 because we received R2 and R3. But here we wasted a bit of bandwidth because we only needed to send R2, we didn't need to send R3, but we didn't know that we would only encounter 1 packet loss. So if we want to use forward error correction with QUIC, we can see 2 different approaches. The first approach would be to do it inside the application, which is on top of QUIC. For example, you can send your application data through QUIC streams or datagram frames, and you could use dedicated QUIC streams or other datagram frames to send some redundancy. So what's interesting in that is that it pushes the complexity onto the application, but you only have a small control on how the data are packetized. So it might be that, for example, you send one source symbols into 2 separated QUIC packets. So you lose that bit of control. The other approach would be to build the FEC inside the protocol itself. So that's what we did. So we use separate frames for the application data and separate frames for the redundancy. So basically, you send your application data through QUIC streams or datagram frames, so we don't change anything there. And you send your redundancy, your Reaper symbols, through a dedicated frame that we call a Reaper frame that we will present afterwards. So here we have a better control on how the data are packetized, because you know which part of the streams are sent in which packets. And it also has the advantage that it can be used by any application which is on top of QUIC. So it doesn't require an additional implementation effort for the application. And finally, it can also protect more than only the application traffic. We could also protect, for example, some flow control frames or any frames that maybe do not even exist yet. So what we did is that we worked on a design and an implementation of a fake extension to a QUIC protocol on 2 different QUIC implementations. So the first one is QUIC Go. So it's working with a Google QUIC design. And we performed the second implementation using MicroQuick on an IETF QUIC design, which was by the time at draft 40. And as we wanted to be generic, we added different kind of error correcting code. So for each implementation, we are able to handle 3 further correction codes. So we can handle the XOR code, the Reed-Solomon code, and the random linear codes, which are currently in the templates. So now we know that we want to protect our data, but we need to define what are our data units that we want to protect. So we need basically to define what are our source symbols. And so there are different approaches. So the first approach would be to use string chunks as source symbols. So you send all your data through a stream, you chop your stream into fixed size chunks, and each chunk is one source symbol. So it was the approach that was taken by the network coding research group until recently. And the advantage of this solution is that you don't need any overhead because all your chunks are fixed size, so you don't need to encode the size of your source symbols. Also, you don't have any control overhead. You don't need to encode inside the source symbols, for example, the stream frame headers, because you consider that you only protect the stream data. But the problem is that you can only protect stream data. You cannot protect other kind of frames that transit through QUIC packets, and you cannot protect, for example, datagram frames, which are now coming maybe into the QUIC design. The other way to define source symbols would be to consider whole QUIC packets as a source symbols. So basically, you look into a QUIC packet, and all the frames inside the packets, you concatenate them, and it forms your source symbol. So it has an additional overhead compared to the precedent approach, because you have, for example, to encode the stream frame headers inside your source symbol. But you have the advantage to be a lot more flexible, because you can protect any kind of frame that you want to protect, basically. And you can also protect the datagram frame, any multipass frame, or flow control frames if you want. So that's the approach that we took, because we wanted to be more flexible for the future. So now we have defined what are our source symbols. So now we need to define how we will send our redundancy. So for that, we designed a new QUIC frame, which is called the Reaper frame. And basically, the frame format is not very important, but what is interesting here is this field, the Reaper fake payload ID. This is a frame field which is opaque to the QUIC protocol. It will only be used by the underlying error correction algorithm to encode some data, and this allows us to use several different coding algorithms without changing anything in the protocol. So that's why it is interesting. So basically, that's why we could use several different algorithms. So now we know how to send the redundancy, but now when we recover some packets, what can we do? Because if we are a receiver and we recover from a packet loss, we could, for example, acknowledge the recovered packet, so that the sender doesn't need to retransmit that packet. But however, it sends a misleading signal to the sender because it won't adapt its congestion control if it uses a loss-based congestion control. We could, on the other side, not acknowledge the recovered packet. With that, the server will adapt its congestion window, but it will retransmit this lost packet, so the content of the lost packet. So that's not what we want, because it will waste bandwidth for nothing. So what we propose is to explicitly signal a packet recovery. So when we recover a packet, we use a new type of frame, which is called the recurrent frame. And this is really similar to a quick ACK frame, but instead of advertising what are the acknowledged packets, it announces what are the packets that have been recovered, so that the sender can remove the packet from its transmission queue and adapt the congestion control accordingly. So now we have all our needed ingredients. So we perform some experiments with our both implementations, and we study a really simple use case, which is a simple request response HTTP use case with different file sizes. And we considered a use case which is the in-flight communication use case. So basically, it's internet inside the airplane. So it's the same network parameters that were presented just before the launch during a previous presentation. And basically, so we took these parameters, and typically this is a really high delay and high losses communications. And we use a seeded loss generator to compare QUIC and vanilla QUIC. So we do a request response, we download some file, and as we have a seeded loss generator, the loss pattern that will be applied during the connection will be the same, and so we can compare the two implementations more fairly. So what we study is the full download completion time. So here it's just a bulk download, so we will compare the download completion time of QUIC versus just vanilla QUIC. So here is a first result. So on the x-axis, you have the download completion time ratio between QUIC and QUIC. So if it's less than 1, it means that it took less time to perform the download with QUIC than with QUIC. And so what we can see first is that with small file downloads, like from 1 kilobyte to 50 kilobytes, there are many cases where using QUIC gave us a big advantage in terms of download completion time. And the reason is just that as it's a really small transfer over high delay communication, if we have a loss, it is likely that the retransmission of this lost packet will occur after we have sent the end of the stream. So if we want to recover from this loss, we have to wait some additional time without the sender sending anything to transmit this loss. So that's why when we use fake, if we send repair packets after we send the end of the stream, we are able to immediately recover from this packet loss. So basically, with high delay communication and short files, the vast majority of the losses will imply tail losses. And with fake, we are able to recover them immediately by using the remaining of our congestion window. If we look at really larger file downloads, like the 1 megabyte file, you can see that using fake with QUIC doesn't bring high benefits. In fact, it's worse. And this is because basically we use a high code rate, so we send a lot of redundancy to be able to recover from many losses. And here, in many cases, this amount of redundancy was too high. So sending this additional redundancy takes more time because it takes more bandwidth. And so this additional time needed to transmit the repair symbols was greater than the benefit of recovering from a potential tail loss. So this is why with big files, using fake at this time was not really useful. So we performed some other experiments with our MicroQuick implementation. And here, as we know that with big files, there is not a big need in protecting the whole files, we decided to only protect the end of the streams that we send. We don't send any redundancy, except at the end of the stream when we use the remaining slots of our congestion window to send some redundancy, some repair symbols. And here, if you take a look at the graph, you can see that the advantage for the curve for the small transfers is still present, but the big disadvantage of fake for the big download has been highly reduced. And this is because we don't send any redundancy, during the whole file download, except at the end. So this is why we reduced drastically the negative impact of fake by sending the redundancy only at the end. We still have some negative impact, and that's due to the fact that we still have some control overhead to signal all of our source symbols, etc. Finally, we decided to analyze the impact of our recurrent frame. So we decided to assess if it was interesting or not to announce that we recovered packets to the peer. So what we did is that we performed an experiment with competing quick flows. So we have one long bulk quick download, and we have 3 candidates for this long bulk download, which we call the background traffic. The background traffic could be a regular quick download. It could be a quick fake sending the recurrent frames. And it could be quick fake, but only acknowledging the packets that have been recovered. And what we study is the download completion time of what we call the foreground traffic, which is a regular quick download, so no fake here. And we study how this regular quick foreground traffic competes with the background traffic. Here in this experiment, we don't apply any medium loss. So all the losses that we saw were due to congestion. So here we can see a box plot, and so on the y-axis we have the download completion time of the foreground traffic, so the regular quick download, and on the x-axis you see the different cases. So in this case, for example, the foreground traffic was competing with the regular quick. Here the foreground traffic was competing with quick fake using recovered frame, and here it was competing with quick fake acknowledging the recovered packets. And as we can see, the download completion time of the foreground traffic is very similar when it competes with regular quick or quick fake using recovered frame. But as soon as we start to acknowledge the recovered packets, the download completion time of the regular quick download is a lot higher. And that is because acknowledging the recovered packet will hide the congestion signal implied by the losses. And so we can see that there was a benefit in using our recovered frame. So to conclude, we can see that first, using packets instead of stream chunks has a benefit in being more flexible, so that we can protect some more than only stream data. We can protect datagram frames or some frames that we have not even invented yet. We also saw that there is an interest in using fake also with short request response use cases. So because we often see the advantage of fake for real-time transfers, but it's also interesting for short transfers in case of high delay and high losses scenarios. And finally, we also saw that recovering packets should be done carefully, because if we only acknowledge the packets, we could be unfair with the other protocols. And we would like to continue experiment in the wild with real setups and also with real-time use cases. So that's all from me. Thank you for your attention. If you have some questions.
Sorry if I missed it, but in the beginning you told that you looked into 3 different algorithms, so Reed-Solomon code, linear codes, or the XO variant. Mm-hmm. In the results you've shown, which type of codes?
So it was Reed-Solomon. So basically we have results with all of different codes. We have a paper with that, but I only show the results with Reed-Solomon here.
How do the results look like for the other codes? Are they better or worse?
So the problem with the XOR code is that it cannot recover from burst losses, so it's the first problem. And the result for the random linear code is that if you have small losses, you can recover from the loss a lot faster, because it's a convolutional code. And if the bursts are very long, it's sometimes better to use a block code, because you will receive the repair symbols more fast. Yes.
Have you, sorry, last question.
No, it's okay.
Have you tried mixing it up, like doing this adaptive? Like, I mean, of course, you said it's interesting for a short connection, but you could imagine for a longer connection that if it comes in bursts, or you have different types of errors, that you start with a more aggressive code and then switch back to a lighter one.
So we're currently working on it. So yeah, but yeah, we continue it. Thank you.
So how many packets are for one symbol?
So one packet is one source symbol, and here in our case here we send 20 source symbols and then 10 reaper symbols. So it's
directly after each other.
yes.
It's not about changing that.
So yeah, so the random linear schemes does that differently. It interleaves the reaper symbols with the source symbols. So it's sends. So if we keep the same amount of redundancy, it would be to send 2 source symbols and then 1 reaper symbols, but protecting more than the 2 previous symbols. So it protects a lot of symbols, but you send it interleaved with the source symbols. So if you have the loss of only 1 packet, it will be recovered really fast. So yeah, it's another way to organize the symbols between them.
So I would say if I would start transmitting recovery symbols at the start of a round trip, that might work better than at the end of a round trip.
Yes, but so here we did the choice of if we have a packet to send, we send it directly and then we perform the coding. So if we do it in the other way, we would have to wait to have a complete block and then do the coding and then send all the symbols. But that's a way to do, and there are also codes that only send reaper symbols. So basically that's your idea, but pushed a little bit further. We only send reaper symbols. Yes.
So I think your conclusion there that you should do it on a per packet basis is a little bit too generalized. Probably you want to really look into QUIC and figure out which information is worth protecting and which information is anywhere redundant and you would have it in the next.
Yeah, so currently we strip out the ACK frames from the packets, and so we are currently discussing with the network coding group just to figure out what should be the source symbol, which are the frames that we would like to strip out from the source symbol. So yeah, that's an interesting topic because we'll have to do that to keep our symbols quite short, to be able to send 1 reaper symbol inside 1 packet. Yes.
2 questions. Is it possible that you receive the recovery frame after the sender already sent the retransmitted?
Yes, it's possible. Yeah. Yeah. So here with code with big blocks. So let's have a visual example. Here we have a block of 4 packets, but if we have a block of 50 packets, maybe we will receive the reaper symbol after the sender has marked 1 packet as lost and has sent a retransmission. That's also why the random linear code is interesting, because if you have small loss bursts, you will recover it nearly immediately, and so you can send a feedback nearly immediately too. So that's why, yeah, there are different kind of code, and some of them are interesting in that sense that you can directly signal that you recovered something.
And the other question was somewhat related to the adaptive case. Could you use the congestion control information to enable and disable the redundancy codes dynamically? So if the connection doesn't have any loss, then you don't send any recovery data. But once you start to notice that packets are being popped, then you start adding.
Yeah. So basically, that's what we are working on.
Okay.
So yeah. So but it's a very good idea. So yeah, it's true. So just watch which are the loss and loss patterns. Yeah.
Yeah.
Can I ask one question? Yes.
No.
There was also, because you mentioned that tail losses are the biggest problem, right? And there was also a proposal for TCP a while ago where you just like send the last packet multiple times.
Yes.
So that would like take the tail loss problem away, and then it would still be interesting how much improvements you get.
So here, for example, let's take an example and just send these 4 packets and then duplicate them just afterwards. If you lose D1 and then you re-lose D1, you are not able to recover it. So if you duplicate packets, fake is optimal in the sense that as long as you receive as many packets as you wanted to send, you can recover the data that's inside. So if you if you want to send 10 packets and you receive 0 source symbols and 10 reaper symbols, you are able to recover the 10. And so it's better than just a duplicate, because if you duplicate a packet, it's not coded, so you cannot you do not recover. You cannot receive if it's lost, you cannot use the other packets to recover the data that was lost. So that's why using FEC in many cases is optimal in the sense
I
that
agree, it's just like if you lose the tail of your packet, because then you run into a timeout that has the biggest impact on your performance, right? So like this is like just sending the last few packets multiple times is addressing this very specific case, but it might already have the largest impact on your performance. Just saying, like, it would be nice to evaluate how much you can achieve under which conditions if you don't look into tailors, because then you're always running a timeout. You know what I mean? Anyway, we can talk later.
But we can talk about that later, but yeah, thank you.
Right. Yeah, this is called Let's Start in Quick Connections. And a little disclaimer up front. So we submitted this last year to Epic and got rejected for various good reasons. I'll come to those reasons later because they're a nice future work area. But anyhow, Robin liked it, so I've got to talk about it. Okay. Let's get started. So how do you rapidly start a quick connection? And well, one of the things that's wrong or not wrong with TCP or QUIC is that you have slow start. So often you have very short website sizes, for example, and all of the time you transmit those websites, you're stuck in slow start and you can't actually utilize your whole bandwidth because you don't know it. So you have to probe it. This is what slow start is there for. And as you can see here, we have 50 millisecond round trip time, and it takes us 300 milliseconds to reach 50 megabits of line rate, which sucks. It sucks even more if there's already, for example, long running flow. You're using QUIC, for example, so the red flow is already hogging all bandwidth, and now the blue flow is entering. What will typically happen is that QUIC sees a loss, and it will exit slow start, and you can see a very long convergence time until you actually reach some kind of equilibrium where you share your fair bandwidth. So that sucks as well. Of course, you could use another congestion control algorithm which works differently. But one of the problems basically that we have here is we don't know our bandwidth that we should, which we should utilize. But of course, slow start is good in that sense because we don't want to cause a collapse of the network. So, well, we're kind of stuck. However, if you look at the second example, you have to induce some loss to the other congestion controller for it to reduce its rate. So you need to be a little bit aggressive, but not too much. So it's kind of difficult, and you have to do it at the right pace. So the idea for us was basically, let's just skip slow start and go to congestion avoidance, but let's just bootstrap the congestion window with an appropriate rate. So how do we get an appropriate rate? Well, it's difficult, but we could simply ask the client to signal it. Because with QUIC now we can actually put something in the packets that nobody sees on the outside, so we can actually deploy something like this. Well, the question is, does the client actually know? It knows all the other parallel flows that it got, and it knows its access technology, and it could know its rate. You might say, I've heard that before. Yes, of course you did, and in that realm, there's another lot of related work. So about increasing initial congestion windows, for example. Currently, it's at 10 or something to have a conservative lower bound, but it doesn't fit all networks. There's other work that looks at learning initial windows from past connections to bootstrap new connections, which is related in that sense that you kind of try to guess a good starting value. There's also something called Quick Start, which uses a pass where you send the packet to have it signal the available bandwidth and then use that. However, that's kind of hard to deploy because you need to change the internet. Very similar, there's mobile throughput guidance, where the idea is basically you have an authenticated TCP option in there, where in a mobile setting, the base station basically puts in authenticated information about the available rate that it sees towards the client. And then there's the one that we are actually basically using, which is Jumpstart, which says basically just pace out all the data. Luckily for us, QUIC nowadays has pacing built in. And basically what those guys back then used was the receive window of TCP to signal the bandwidth, because this is the only thing you have left in TCP which you could use for that if you're not using an option. And there's an addition to that called Halfback, which is basically something like Mirja said earlier on, which opportunistically retransmit the tail, which often gets lost. Yeah, but basically we wanted to see how well can QUIC cope with such ideas, which is basically Jumpstart, which we did. So we kind of assume that congestion happens at the edges, which is of course not always true. But let's assume it's true. So if we're at the edge, we could, for example, do client-side bandwidth estimation by looking at our wireless. So if we are connected via Wi-Fi or something, we can easily calculate the fire rate using the current modulation scheme, which is typically available on all operating systems. And from that, you can easily calculate an application rate. Similar stuff you can do with mobile, for example, with LTE. If you know your bandwidths, band modulation and MIMO, you can calculate a fire rate. If you're connected via Ethernet at home, you can, as with everything else, you can use past maximum speed measurements to bootstrap that. Or you could, for example, ask your local gateway. There are protocols. People often know TR069, which is the external protocol to configure a gateway from your ISP, but there's also an internal one, which you could use, for example, to get your current transmission speed towards your ISP. However, we did not investigate how well any of those work. We just assume that there's a way to estimate bandwidth, and we will look at how bad it gets. So we will look at what happens if we have a bad estimate, but we don't know how well any of those will work. So to see what will happen with Google QUIC, we modified Google QUIC to basically have the client signal in its initial packet a bandwidth estimate. And the server uses that bandwidth estimate and an RTT sample from a previous connection to calculate the bandwidth delay product, and uses this to bootstrap the congestion window and directly go to congestion avoidance. And we let it compete with an unmodified Google QUIC, which uses cubic congestion control with initial window of 32 and has pacing. There's a little difference. So if you use pacing, typically, if it's in slow start, it will pace over half a round trip. If you're in congestion avoidance, it will pace over 75% of a round trip. Yeah, we'll use Mininet to evaluate various network conditions, so we know the true available bandwidth, which we can signal and which we can also not signal. And we measured the flow completion times for a small, a medium, and a large file, basically, which is motivated by a website, a video chunk, or a whole large website, or just some larger file. And then we announced simply true bandwidths, half of the bandwidth, 1.5 the bandwidths, and 3 and 4 times the true bandwidths. And we let it compete against a single elephant flow, which already hogged all the bandwidths. And we see what happens. And then we, well, repeat that a bit and see what happens. Now there's a large table, which I won't go into detail, which basically shows I can do tables with LaTeX. So it's just an example to have it on the slides and show you. So we have various settings, for example, a slow DSL setting with 25 megabits. And here you can see a green arrow that's pointing up. If we have an improvement with announcing, in this case, 0.5 times the true bandwidth. The arrow is orange if it's actually in the same RTT, because then it's basically just because we have different pacing aggressivity. And we basically show the flow completion time as well as the losses. So an example you can see, if we announce 0.5 times the true bandwidth for the 70 kilobyte case, you can see that the losses are reduced by a factor of 4. However, our flow completion time increases by roughly 50 milliseconds. For the 2 megabyte case, it goes down by 170 milliseconds. Yeah, well, Sometimes you can't decide if it's better or not. And what you can generally see, the more you overestimate the bandwidth, the larger your losses are. But of course, since you're very much overestimating your bandwidth, you will also put a lot of packets in the network, which leads to you hogging the bandwidth. So also your flow completion time will typically go down if you're not overly aggressive. So you're basically buying shorter flow completion time by losses and also by using losses at the other end. Well, you can do that for faster DSL, for 3G and then LTE, and now you can't read that because that's just too much information. So let's just focus on one smaller case, the DSL fast case, and here you can see a lot of CDFs. So basically, small file, medium file, large file, and from left to right, it's basically flow completion time, fairness, which we want at 1, and the number of lost packets. And you can, so if you want to focus, you can focus on the red dashed dotted line and the brown dashed dotted line, which is the regular QUIC compared to, hey, we guessed right. And what you can basically see, for example, can I find something here somehow? Yeah, that's great. So what you can basically see here, if we use the regular QUIC, you can see that the curve is not very steep. So there's a lot of variation in these results, which basically kind of corresponds to what we saw earlier. Sometimes Losat is able to get the bandwidth, sometimes it isn't. You can see with the estimates, the curves are a bit steeper and typically more to the left. What you can also see is we overestimate the bandwidth, our packet losses are kind of high, which we don't want. And if we overestimate, you will have significant losses. If you take a look at what we saw earlier again, so this is an example where we took the best regular QUIC flow and compared it to a medium-sized flow that we started. You can see it's kind of okay. However, if we take one of the medium-sized bits, so where we guessed correctly, you can see it much quicker reaches an equilibrium and also it much quicker finishes. For LTE, it's kind of similar. The only difference is that in our LTE network, we have larger buffers, which, because we use QUIC, tend to be full. So if we overestimate our bandwidths here, it's typically not as bad as we would. We have smaller buffers because those buffers basically we don't calculate, so we don't have them in our round trip estimate. And that's why if we overestimate here a bit, it's not very bad. This way we can still get better results if we have slight overestimates. Well, these results look kind of nice. However, we did only consider one flow that is competing, which is questionable how realistic it actually is, right? And what would actually happen if we have multiple flows? Would we actually still announce the full bandwidth, even though we kind of know that there are already 4 flows that have each 1/4 of the bandwidth? So what if we have multiple flows in parallel? For example, if we discover a website and subsequently those flows start to request data, would you always have the same? What would you announce to them? So you would need to want to measure that. You also want to see how different congestion controllers react to doing that, because not all react to losses. And of course, how accurate would real-world bandwidth estimate actually be? The client could also lie about her bandwidth estimates, right? So I know I want to have a good performance. I don't really care about the losses that the others get. So I could just cheat and announce something very large, so my website loads faster. Of course, the server could see if it kind of fits to previous measurements. There's also maybe concerns. So if I would do bandwidth estimates, how much privacy-related information is actually in those bandwidth estimates. So if I travel maybe from Aachen to Köln, and I have a LTE connection, it goes down, goes up, goes down, and goes up, and I'm continuously reporting that to a server. Could he maybe know where I'm traveling just from bandwidth estimates? So it might be privacy, a privacy concern. You could also ask, could you use the bandwidth estimate differently? So for example, in the earlier examples you saw, when the one flow exits, basically the red flow remains in congestion avoidance, even though we know that the flow left. So couldn't we actually signal him via our bandwidth estimate, hey, there might be more bandwidth available now, and you could maybe try slow start. Yeah, so we basically revived an old idea, which can be easily deployed with QUIC today. It works very well in easy settings. However, you need a so the bandwidth estimate must not be off. However, it's questionable how real world applicable that is. You must test it with more flows. Well, yeah, there's a lot of future work. So that's it. Thank you. You may ask more questions, or I have more concerns.
I do think it's an interesting topic because it's a big problem and people were like shying away about, because like all solutions have drawbacks. So good luck.
I don't think it will be something that will end up in some standard, but depending on what your application area is and what kind of devices you control, you could still think about doing that.
So I just thought, because we had the previous talk, if you combine this with for error correction, right?
Yeah.
It could be really useful, but then you also have the fairness problem. So I don't know.
Yeah, I don't think it's applicable at large in a way that you would make it like something internet default. But if, I don't know, I'm a big CDN, I'm doing live streaming or something for my customers, and I know they don't do anything else on their mobile right now, that might be something I want to, or might want to have. Yeah.
One of the things that I want to look at is doing this, but only for like the very first flight, like the 0 RTT. That you can like have, I know what website I have, I know the exact resources I need for a full first payment or like a full first load. I'm going to blitz them all over at once, and then I'm just going to do normal slow start, normal congestion control after that. So a very big burst in front, and then all the rest after that. What do you think about that?
So we're not modifying the rest of the congestion control. We're only, so it would be kind of similar, setting the congestion window to whatever many bytes you need to push that information out, just without the client telling you that this might be a bad idea. But apart from that, we don't change. So if we see significant losses and have a timeout, we will go back to initial window of 32 and do slow start. So we don't change that. We just basically change. We just skip the first slow start and go to congestion avoidance, but don't mess with the regular logic that's there. All right, then thank you very much.
Any first step idea?
Okay, I'm presenting slides one of my colleagues presented at the last IETF meeting. That's also why my name is not on here. But like, if you want my email address, right, I can still tell it to you. It's not like I'm hiding it. And so what we're interested in is like how getting some kind of measurement information from a network point of view. Like if you're in the network, how do I know what those flows are doing and how they behave, and like if my network does the right thing it should be doing. And with QUIC, you have much less information than with TCP. TCP, you have all these nice things like the timestamp, the sequence numbers, and so on. And if you look at them, you can actually figure out what's the loss rate of this flow, what's the end-to-end round trip time. And with QUIC, you don't have this information anymore. So there was a very long discussion at the IETF to provide at least one bit to the network to actually provide some of the information. And this one bit is called the spin bit. And it can be used to infer the end-to-end round-trip time between the two endpoints. So the way it works is just like the spin bit spins once per round-trip time. So if you observe it from the network, you see like a row of zeros for like one round-trip time, and then a row of ones for another round-trip time. And if you just look at the points where you switch from 0 to 1, you can actually measure the round-trip time of that flow. What you would do with information is like you have different observation points in your network, and you actually measure the round-trip time on a per flow basis or for an aggregate. So it could also be that multiple flows multiple flows are running through your router, and you might just want to have an aggregate to figure out if there are big changes in round-trip time, for example, because there's happening something in your network. Usually what you do is also you observe this information in multiple points in your network and then send this to like a central collector and then compare this information or do additional or derive additional information from it. So what one of my colleagues did, who did this presentation, actually was like writing a quick implementation to actually get this information from a flow, which is called spindump. And like his question was also like, how do we want to represent this information? And his requirements was like getting something that you can like export easily and collect centrally, but it's also human readable and provides you all the information you want. And so he made up his own little JSON-based format. And actually, it doesn't matter that much what the exact format is. But like having all this discussion about this thing, it was also some thinking was also nice that it would be nice to use the same kind of format not only for network monitoring, but also, for example, for endpoint debugging and so on. Of course, at the endpoint, you can have much more information because you can look into the packet eventually and export more information. But just having the same format allows you to use the same tooling to actually analyze the data you get. And then also, there are different methods, like, for example, IPFix, where you export flow information on a frequent basis and so on. But it might also not exactly be what we want, or it could be adapted to what we want, no matter, it's not human readable, but the idea here is also that you want to not only have flow information, but you also want some kind of event-based information. Because what you want is not only the average round-trip time of your flow, but you want to observe the round-trip time over time, because you actually get one round-trip time sample per round-trip time. So over time, you get multiple samples and you can actually see changes in round-trip time, which might be particularly interesting for your network because you can see when something happens in your network. So this is just some plot I got just now from one of my colleagues working on this, and it doesn't have access there and so on, and it's not great, it's not well readable, but just to show you some data that there's something doing. So what you see here is just the measurement over time. And you see the round-trip time that we measured at different points, and more exactly, you actually see the round-trip time difference. So we have a setup here where you have a client, and then you have two measurement points, measurement point 0 and measurement point 1, and then you have the server. And then the blue line, or actually the green line, is what we measure between the client and our measurement point 1. Then the blue line is what we measure between our measurement point 0 and measurement point 1. And then the orange part is between measurement point 1 and the server. So we can see that actually the round trip time from the client to the first hop and between the two hops is quite stable, but the round trip time to the server is where kind of the issue is. And we can do this with spin bit because the spin bit can not only measure the end-to-end round trip time, but you can also measure the round trip time on both legs. Like if this is your observation point in the middle, you can actually measure round trip time from here over the server back to you, or from here over the client and back to you. And just because you can subtract this data from each other and you can collect this data from multiple vantage points, you can actually look at the round trip time of a certain leg. And I have no idea why the round trip time behaves so weirdly, why there is so much delay at the beginning and then it goes down. And I tried to ask my colleague and he wasn't sure. But it's just a simulation, just like testing our tool here. Somehow it's a very low bandwidth link and there might be some congestion or whatever, I don't know. Okay, so like this is a very short presentation just to say that there is a different use case for logging data, not only for like debugging and analyzing your code, but also for network monitoring. But it would be super nice to look at the same kind of formats and use the same kind of formats. What we have different requirements because we need to combine information from different sources, or it can be useful to combine information from different sources because that gives you additional information about your network. And then there are, of course, open questions about, like, because you have to transmit this data, like you want to compress them somehow, and you have to anonymize the data and so on. But I guess that's the usual stuff, actually. That's it. Any questions? Or was everything crystal clear? I guess Robin is talking more on this topic anyway.
Is there anything else that you can measure besides the round trip time, or only the round trip time that's measurable?
Sorry, can you say it again?
The spin bit.
Yes.
You can only measure the round trip time, or are there other things you can derive from it?
So yes and no. I mean, like you can because you see. Or you have to also kind of use some heuristics to figure out if the sample that you see is valid. Because if you see reordering or losses, whatever, then the edge where you actually make your measurement might show up somewhere else than it actually should be, because exactly that packet got reordered or whatever. So what we do in our tool is to have some heuristics to like filter out the not valid samples. And that actually gives you some additional information about how good your network is. Like there might be some reordering losses that gives you invalid samples, and just because you have invalid samples, you can derive some additional information. But the more you derive from something, the more gross the information gets, and it's not sure if that's actually useful or not to us. But it might just give you some indication, then maybe you have some other tools to dig deeper into it.
Right. Thank you for listening to me talking about logging again. But I think it's very important. That's why I keep coming back to it. End of last year, I wrote a blog post where I kind of tried to look at some of the challenges that QUIC is facing and actually getting deployed in practice. A lot of that is political, are people going to allow QUIC on the networks, that kind of stuff. But a lot of it is also technical. One of the points that I made was that QUIC is actually kind of complex. It's so complex that we had to split the protocol into 2 versions already. Like a lot of the things that we talked about today have actually been postponed to version 2 because they were just too difficult to add in version 1. And even with those things removed, version 1 is still plenty complex. There are a lot of things, even all the obvious complexities that can lead to a lot of subtle differences in implementations and the impact that they can have. There's also the case of exposing this to your developers.
right? This is a very complex protocol. How will the higher level APIs will look for people who will actually use that? One of my favorite anecdotes for that was for HTTP2, where I've heard of developers that said, we have these big files, we're going to cut them up into small pieces because HTTP2 is faster for a large amount of small files than HTTP1, which makes absolutely no sense whatsoever. But people misunderstand what HTTP2 is actually doing. They just hear about the marketing speak from companies like Google, and then they try to extrapolate into what they should be doing at the higher level. So educating those people is going to be difficult. And I have kind of a bit of a confession to make. I mean, even for us, QUIC is very complex. When I'm saying here in the middle, I think it's true. I think there are very few people worldwide now that really, really understand all the ins and outs of QUIC. Most of them probably part of the QUIC working group. If you really want QUIC to become the major transport protocol, really take over from TCP, you're going to need a way to get people like students and researchers and of course also application developers into the protocol. You're going to need ways to get them up to speed quickly. That's one of the things that I've been focusing on for my work is how can we do that? One of the ways we do that is like this. So we have our own QUIC implementation. It's in JavaScript. Well, it's in TypeScript, so it's a typed version of JavaScript, thank God. But still, I do this not because I think it's a good idea. It's not. I don't think it's going to be used in production. It's more like I want to have an accessible code base that people in their third bachelor can actually start looking at and interpreting what the protocol is doing based on the code. If you have to do that with a hyper-optimized C or C++ code base, it's going to be a lot more difficult. I currently have 2 bachelor students working on this, one in HTTP3 and one on congestion control. And while it's not always all that easy, it's going. They're able to make progress. They're able to understand what they're doing, which I think is quite impressive for a third bachelor for a protocol of this complexity. The second thing next to this, of course, that we're doing is the tooling. We started creating tooling with HTTP2, which helped us a lot then. And so we tried to do this as well for QUIC. Now for HTTP2, we mainly relied on PCAPs, so TCP and Wireshark, TCP dump and Wireshark traces. But those don't always contain all the information you might want. Like for example, here you have one visualization that's actually mapping some of the congestion control information. That's not available on the wire. You can only get them from endpoint logs, endpoint state, which is something that's not typically done. And so the way we started doing that is one of my students, he took the actual output logs from 4 different QUIC implementations and wrote custom parsers for these into a single common data structure to be able to compare them in a web-based tool. Don't worry, I'm not going to make the exact same joke again. I've made this 3 times already. But so that's very, very tedious to be able to do that. So we created a couple of tools that way, and it was just not very productive. That's why we said, look, what we really want is a single standardized logging format that you could, if everyone outputs the same logging format, it's very easy to just aggregate that, write reusable tools, and then share not only the data itself, but also the tools in a very simple way. That's kind of what we proposed in our paper last year. We called it QLog. It was very simple. It's just a JSON thing because we are making web-based tools, and web is very easy to use with JSON. That's the main reason for doing that. It's also nice and human readable. Some of the things that are in QLog is that we have like what you would see in CSV as column names on the top there. And we split out category and type so that we can very easily filter on larger scale. So we can, if you're not interested in HTTP3, you can just drop the whole application layer category, for example. Another thing that we introduced was trigger. The idea is that why does an event occur? Usually it's clear from the context. Let's say that you have an event, a packet was detected as lost. If the previous event in the log is we received an acknowledgement, the loss is probably because the packet was not in the acknowledgement, right? That makes sense. But you would need to do a lot more work in your tools to be able to use that context. If you have an explicit trigger, it's much easier for the tooling, it's much easier to do. searches for a specific type of triggered events. The last thing that we had was, of course, every event should have any type of data associated with it. So we proposed this for QLog. We proposed this for QUIC, got some good feedback. And then Mirja, she came back to me on the mailing list and she said, why would you only do this for QUIC and HTTP3? Can't we do this for other things as well? Can't we do this for TCP, for other streaming protocols? At that point, I started thinking, doesn't that already exist? Don't people already do that, right? Isn't there a way? How do people currently do tooling? And apparently, it's worse than I had imagined. As far as I can tell, I hope I'm wrong, but as far as I can tell, most people just use PCAPs for debugging. And if you're doing web performance work on a bit of a higher level, you basically use it browser dev tools. They don't even have any of the TCP layer information in them anymore. They just have only the HTTP layer information and sometimes not even that. I do know that a lot of the bigger private companies like Google do have their own internal tooling. It's not open source. It's very tuned to their use cases, very tuned to their logging formats, which are also not open source. And so what I've seen in the previous years is that, especially in academic work, people are not using a lot of tools. And there have been a lot of papers, especially in HTTP2, where I have serious doubts about the validity of their results and their conclusions on the results, because I'm sure they have not been looking at TCP level traces of what is actually happening on the wire. It's not just academics though. This is from a work on HTTP2 prioritization in the wild as being done by CDNs and hosting companies recently. And this is actually you can very clearly see that that a very few amount of public HTTP2 implementations correctly implements HTTP2 prioritization. I think a large part of that is just because people deploy it without looking at actual logs because there are no tools. And I really hope that the bottom statement is not true, but I fear it is. I know it is for HTTP2. Very few implementations, not extremely well tested, and people just use it without knowing what it's actually doing. And I hope we can prevent that for QUIC. So at IETF, we discussed this, maybe doing this as a separate working group already. It was deemed that this is maybe a bit too early. So we split up the whole QLog stuff in two different drafts, two different efforts. The one is a high-level schema. The idea is that that might eventually evolve into something protocol agnostic that we might reuse for other things as well. And the second one just uses that basic schema and maps QUIC and HTTP3 semantics on top of that. That's kind of, we're hoping to evolve the high-level schema enough to build some other efforts onto that eventually. So I wanted to the rest of the talk is mainly going to be how do we take the basic QLog QUIC specific things and add stuff to make it more general for other things. I'm not going to go over this because I'm going to give examples for most of these main tenets. The first thing is flexibility. The first QLog proposal had on top, you had the 5 fields. And basically every log would have the same 5 fields. Here we're saying, we're going to split that out into what we call common fields and event fields. Common fields is the idea that every event will have this field. So if you have a single trace, all of it is QUIC and HTTP3 traffic. It's just an entry in the common fields. Every event, of course, also encodes its time relative to a certain start time that's also in the common fields. This is a nice way of doing things because if we have the example of Mirja from just now, if you have a log containing multiple protocols, you just remove those fields from the common fields, you add them back into the event fields. And you start logging per event which protocol you have. In this case, you also log, for example, the 4 tuple. In the previous case, we had the QUIC connection ID in the group ID field because you can group all the events together on the connection ID. And then here you could group them on the same 4 tuple, for example. So you can be quite flexible in that way. Now, what you can see here is if you have hundreds of events like this, you're going to lose a lot of file size. You're going to have a huge file size because you're constantly logging the same 4 tuple. So the next thing we added was if a field is in both common fields and event fields at the same time, it means you will reference by index. So here if you have index 0 for protocol type, that means the first entry in the protocol type value array. And that way you can do a simple reverse lookup. This is actually how Chromium browser currently logs its internal logs. I think for these two fields, it actually makes things more readable. But if you would extend this to things like category and event type and trigger, it will become much more difficult to do this in a human readable way. It might be a nice way to save on file size, but you sacrifice on readability. We can go further, which is also proposed, because we can save as much as we want on those initial fields. If you have data that is still repeating all these keys as well, you're going to lose a lot there. So you could go to a fully self-describing format, where you have in the header, again, if this is the type of event you have, these are the fields that we expect, and then you can skip logging the keys again. You can go 2 or 3 extra levels deep, I think, in this way of reasoning. The question is, where do we stop, right? For me, I think we stop before we do this. I think this is kind of where I would like to draw the line between extensible and pragmatism. But it's an interesting thing to discuss and to get some feedback on. The second thing is streamability. So what you really want is things like live debugging. You have a live deployment, you want to know what's happening in the current connection, whether in an actual production environment or in a simulation, so that you can live tweak some parameters. So you want the format to be streamable. The current way is set up with the different events. That's perfectly possible. The only nasty thing is that JSON parsers normally require everything to be nicely closed. So those 2 characters at the end really have a big impact if you try to parse the file without that. What you could do is have a post processor adding that, for example. But what we have been doing is using a streaming JSON parser. Those are available for most programming languages and frameworks. That works quite well enough, and you just get a new event, for a new callback for each individual event that you get. And it just works quite nicely. So I think that's an acceptable solution. Another thing that we added is that a single QLog file can contain various traces. What we're doing this now is mainly splitting it up by what we're calling vantage points. So in this case, this is kind of also what Mirja is showing, is you have multiple points in the network where you're measuring. In this case, we have a client, 2 points in the network. In this case, it was a CDN concept. So you have a caching server before the actual edge server, and then you have an origin server. You will log at each of these individual vantage points. What you can then do is aggregate these logs into a single QLog file, combining them into one, and then you have a single file that you can send around to other people, interpret, load into the tools, and look at what is happening end to end in the network. I also think we have some people here that are doing a simulation framework. I think this kind of thing would be excellent for that. But we could also do, and that's what I had before, if you want to log, like so let's say TCP and QUIC in the same trace, you could also just split them out into 2 traces. You can have a single trace that's doing all the QUIC stuff, a single trace that's doing all the TCP stuff, and still have them in the same QLog file. The second thing that's that I really like to have in there, and that's lacking in a lot of logging formats, is support for tooling. So the first field that I have is inspired by a CDN, where they said, we typically have hundreds, thousands of different traces for each endpoint at a given time interval. I want to very quickly identify the most interesting of those, the ones that had packet loss, the ones that had low throughput, the ones that had congestion control problems. So what you could have is at top, like a summary field, having some kind of interesting information about what is in the rest of the file. You combine that with a streaming JSON parser. You can just read in only the summary fields of everything, decide which of these you want to load, and then load the full file if it's interesting enough. The second thing I'm very interested in is configuration, where you can indicate, for example, settings from tooling. Let's say you've loaded in a trace or a couple of different traces into a tool, and you've zoomed in on a particular very interesting case, and you've tweaked some settings, you've tweaked a color scheme, you've highlighted a couple of things. You want to send that exact view to your colleague, for example, for further debugging or further interpretation, you can take a screenshot, but it's better if you can just say, load this exact file into the exact same tool, and you will see exactly what I've been seeing. This also makes things like research a lot more, I think, reproducible or at least reinterpretable if you can support these kind of things. Then I also have transformation friendly. A lot of people have said, this is JSON, it's going to be slow, I'm probably not going to output this from my implementation directly. And I made a comment there that I'm not entirely sure that I still stand behind, but still, that QLog might not be a common logging format, it's more like a common input format for tools. So it doesn't really matter if you log something else from your implementation, as long as you have, these converter applications going from one format to the other, as long as you can do that, which is actually what most people are leaning towards right now, we can still have a nice application for QLog, even though there are, of course, already also implementations that are outputting QLog directly, for example, the Lightspeed implementation. So next to all of these, there are still plenty of open questions and discussions. The textual versus binary always comes up. The trigger field is one I really want to discuss further. Is this useful? It's very difficult to implement in practice because you usually don't have that contextual information. So is that worth it? How would people use that? Is it really worth it to have like 20 different something to QLog converters? Does that, doesn't that undo the usefulness of a single standardized format? Right? At IETF, I thought that was a bit surprising, but a lot of people were very interested in the privacy question. If you start logging at this case, and it's very easy to load and share these logs, what about privacy? What about personal information in these logs? And then something we talked about earlier before is like, can we actually support everything in a single format? Because even within QUIC, you have a lot of different use cases, and maybe a single format cannot simply support all of those. If it can, then why doesn't it exist yet? Right. So those are some of the questions I have. The last question is the most important one. Input on that is also very appreciated. So I have 1 minute left. Fantastic. Well, not so fantastic because I was hoping to do a small demo of some of our tools, but I don't want to go too much over time if people are not interested in that. So is there anyone who doesn't want to see a demo of tools and would rather just go to the discussion? I know it's a sucky thing to ask, but
just do the demo. The discussion takes more time than showing the actual demo.
All right. So this is a timeline tool. It's just this is 0 milliseconds. This is 10,000 milliseconds, and we're just plotting every individual packet on the line here. It's every the packet is color-coded based on the most important QUIC frame in it. In this case, it's an ACK, so the green ones are ACKs. The nice thing about this is here I've loaded 3 different traces. So the top one is the client trace, then you have the server trace, and then you have the T-shark, the in-network trace. Some of the things you can see here is that, for example, here the server is sending everything at the same time. The network is doing the pacing. So we set up a TC pacer, and that's very clearly visible here. That's very different from here at the end. Here you also see, it looks like pacing here as well, but you can see that the server send is actually doing the pacing itself in the QUIC layer, not in the network layer itself. This is a scenario where around here the network is completely cut off. And if you would only have the Wireshark view, you would not be seeing that the server is actually trying to retransmit stuff. And how much and what is it trying to retransmit. So having additional endpoint state in this case is also interesting to see that. What we can also do in this implementation is change colors. So here, let's say I'm mainly interested in flow control. I'm trying to debug flow control. I can only highlight those frames in this case. This is similar, what we can do. So this is the UDP layer, everything aggregated. We can split it out per stream. And if I told you that the pink squares are padding frames, so 0 padding frames, you would probably think that's not right. Why does every single packet that you send contain a padding frame, right? It could be a major bug, or it could be because they're trying to do something clever, trying to hide the real size of individual resources, which is something that was added to HTTP2 for Apache recently. But just seeing it like this, it makes it incredibly clear that there is something going on there with the padding. It's clear one oogopslag, right? I can't find the English word. I had a different, yeah, I'm just gonna skip it. So yeah, then we have this one. I'm actually very happy. I'm very interested in how this could work, but I'm very unsatisfied with how it works at this point. Right? So here you have, again, one endpoint, the second endpoint, and because we're doing that, we can show exact latencies. The slant of the arrow is the exact latency that you saw there. But you can see that here we start experiencing higher and higher and higher latency. On that, let me see if I have the one here. So here, for example, we have a couple of things are sent, and then we wait here until we have a max data. So we have flow control update stream, which only arrives at timestamp 58. And this is 34. This is one of the challenges that I have with this tool. If I had the actual time difference between 34 and 58, you would have a very long page, mostly containing white space, right? So how to make it clear that you have these latencies and slanting of arrows while still keeping a usable tool. There's another thing here where here you have a lot of reordering. So we add a lot of jitter to the implementation. This is useful seeing, yes, there is a lot of jitter. It's completely useless in determining what effect did this have in practice, right? So I think this kind of tool has a lot of potential. We're not there yet. What I'm trying to do now is, so this is just 2 endpoints. What I'm trying to do now is trying to make it agnostic for as many endpoints as you want. So if you had the aggregated QLog of 4 different vantage points, you would have them all into a single visualization, so you could track everything between, and then you could have the same kind of logic that Maria showed, where the delay that we're seeing end to end, where is it coming from between which endpoint? You would see it just by looking at the slant of the arrows. Then we have these ones, where here we're showing the data for each individual stream. So this is, every stream is sent. And that means that if you have an overlap on a y-axis, that data is retransmitted, which is very weird. Why are we retransmitting data here? Why is this data being retransmitted? Because I'm not really seeing any loss events at this point. Is there something wrong with our congestion, with our timeout implementation, or are we putting our handshake timers too aggressively and stuff like that? This also shows again that we have some severe troubles with overlapping data, because all of this is sent at the same timestamp, but we can't show it on the same timestamp because you would lose. You would not see that you have different streams going on. The same here. These actually all have the exact same flow control limit, of course. You can't plot them all on the same line because you would lose that information. This one is more complex, where we actually do have some loss, where you do find it easy to follow how the congestion window evolves over time. One of the things I find interesting here is that these 2 streams are being postponed very late. So we are giving preference to all of these previous streams. All the retransmits that are happening here are getting a higher priority than the 2 later frames. the two later streams. And depending on the application and the prioritization setting, maybe that's what you want, maybe that's not what you want. But in this kind of visualization, it becomes immediately clear that this kind of thing is happening. This is one of the most recent ones. It's inspired by the tool that Google uses, and it also looks a lot like TCP trace, where each of the blue ones indicates data being transmitted. So this is again data going up. And then the green ones are the acknowledgements. So if I have this green one here, that means it acknowledges this original packet. This means that the distance between these two is actually our latency, end-to-end latency between sending of data and receiving of the acknowledgement. We then also plot again the same congestion window, Bison flight, and then here the round trip times. And that gives some very interesting things with some more complex traces here. For example, here you can see very clearly the round trip time going up because of the interval goes higher. You also see this happening here, of course. Then you have loss events doing something to the congestion window. Additional loss events do not do something to the congestion window. Maybe that's what you want, maybe it's not. Then you have some very weird quiet spots in your connection. Again, maybe that's expected, probably not. So having all of this, especially for these more complex long-lived flows in single major view, I think is very, very useful. Yeah.
So did you compile all these plots from the same input file, or did you actually collect different input files with different information for different scenarios?
Every single thing you've seen up to now has been different input files. So we collected some ourselves for the initial studies, and these come from several people. I think this is one from Fastly, and the previous one was from Google. So this is really from the real QUIC implementation and what they're using for debugging their congestion controller at the moment. Then this one, this is actually our oldest tool here, but this was for HTTP2. So this shows your HTTP2 prioritization dependency tree. A lot of people, when they visualize a tree, they will show you just something like this, which is not really correct because the tree is actually built up all the time. Nodes are discovered, they're added, they're removed, and then new nodes are added. So it's not like if most people just show you this kind of tree, it's not that they're all competing for the same bandwidth at the same time. It's a long and flowing process. So this kind of tool really helped us understanding what was happening in the different scheduling choices from different browsers for HTTP2. And we're planning on making the same thing for HTTP3, of course. And then the last one, I promise, is actually my favorite. It's the newest, and it's already my favorite because it's the simplest one we have. It literally just plots the data frames for individual streams, and each stream gets a different color. That's it. That's all it does. Yet, it immediately becomes clear what is happening on the prioritization logic. So even without looking at the file name, you can see this is a first in, first out, right? First stream sends all its data, then the second, then the third, then the last one. Immediately clear.
How did you read it, like row by row?
Yeah, it's just row by row. So row, then you wrap to the front again. I'm sorry. I said it was simple. Right. And this then is also very easy to interpret. You have a stream, it sends entirely, then the next stream starts. Suddenly, a new resource is discovered that has a higher priority, a higher weight than the green one. It interjects itself within the stream, gets all the bandwidth until it's done, and then the green one continues. This is actually the behavior that Google Chrome has at the moment. Again, you don't need complex visualizations, you just need colored divs. This tool was could be written, let's say, in half an hour. This one is a bit more interesting. It's showing a round robin, purely fair round robin, as I should say. So each has the exact same weight. So what you would expect is to have the exact same sequence of colors after each other, right? Always the same exact sequence, because that would be fair. But it's actually happening, and we have 4 streams, which are actually obvious. You have the first 4, and the last 2 are repeated. So red and yellow. Then you have the 2 next ones. Those are repeated. Next ones, those are repeated. So there's apparently something wrong with the implementation of the round robin scheduler in this case. Maybe, maybe not. Probably there is something wrong here. Again, immediately clear from just looking at this one. Here we have a more complex one. It's also round robin, but it's weighted. So here you do have different weights for the individual streams. So the purple and the red one are the most important ones. They get the same amount of bandwidth. Only when they're done do you start seeing the yellow and the green one. Now, except for the first 4 ones. Right? First 4 frames that we send is 1 for each stream, which is not entirely logical. Why do green and yellow get bandwidth, even though they have such low weights? And so that also turned out to be debatably a bug in the implementation, how the implementation was done. Again, very simple visualization, making that clear almost immediately. So final slide. Just as we had a lot of open questions about our logging, we also have a lot of open questions about our tools. Like I've shown you, we have some very nice things. We also have some things that I'm very doubtful about that we should improve. How do we handle overlapping data? That's very difficult. Are we going to go to like having hundreds of very small tools like the last one I showed you versus like 3 or 4 mega tools that do everything at the same time? One of the most important things, first red item, is because QLog is so flexible, so it can provide you with any type of event and any type of category, tools will probably need a way to specify which of those events it's actually using. So let's say if you want to use me, you will need a QLog that looks like this, or you will need to log events that look like this, because otherwise we can't deal with all the flexibility. So some of the things I want to hear from you in the discussion is what kind of tools do you use today? What kind of tool would you like to use? What is your ideal tool? What doesn't exist yet? And for example, for multipath, I've been thinking about it. How do you debug multipath?
Printf.
Right? Exactly. Like, I cannot imagine that you can create a working multipath implementation without bugs just using pcaps and printfs, right?
I think we cannot imagine it.
Yeah. So, what type of tools would be useful for that? How might that look? I think it's something that I would like some input on. All right. Thank you. That's it for me. If you have any questions. Again, a very clear talk. No questions? Oh.
Yeah, I kind of like it because it's so. If you use stuff in TCP, Wireshark is kind of your friend because it has nice visualizations and it's a bit mixed about it. But Wireshark has this. It misses out what the actual implementation does, right? The events. Typically, I try to mix Wireshark or pcaps with eBPF output that I dump from the kernel, which is, of course, in a different format, but then I do custom stuff, so I like that. But so when you started about how the format should look like, I was like, he's converging towards a pcap-like file. I wouldn't worry too much about file size and compressed stuff.
I agree. People on the mailing list do not.
Because I tend to scroll through these files and look for something there.
So 2 points. One is on the, I think on the previous slide or on some slide you asked why wasn't it done yet?
Yeah.
Why doesn't it exist yet? Because it's very complex. People only focus on like their specific use case, right? But I think there is still a huge value because you have like a large set of tools on the one hand to show the results, or you might have a large set of tools in the future, and you have also a large set of tools to collect this information. And at some point you need like this cross point where you can actually make one work with the other, right? And that's where the value comes in. And it doesn't really matter that much what the exact format is. I would argue, I think it should be human readable, because the compression part you can be somewhere between here, right? You can
Sure.
collect it in a binary format and then transmit it and then convert it. But the important part is that you have a format that actually covers all the use cases on both sides. So, and you did this to some extent because you talked to a lot of people and people have different use cases, but stepping back and looking at the different use cases and figure out what the requirements are and what the requirements are you need to support in this format and not in this format or this format. Is probably a useful exercise to do. Like, for example, what I have in mind also is, because in the ITF, we usually look at communication protocols, not only formats, is also the question about how to share this information in a useful way, right? How to make sure, and that's like all the privacy questions you got, how to make sure that people can access information they need to access in a secure and maybe authenticated way, and how to like make sure that like only the part of information that like is important for this entity is accessible by this entity, and this can be converted in these kind of questions.
All right. Thank you. That was the last talk. So, changing hats. That's kind of it for the well prepared, thought out section of today. Right now, the idea was to go to group discussions. That only works if you have a couple of groups that want to talk about the same thing. I've been thinking about it, and I haven't really found a good way to have people do that. If you know what I mean. Like, do you want to get up and write a topic on the board, and then people put their names next to it, and then we congregate like that? Like, for example, I would be very happy to talk 2 more hours about logging. Obviously, right? Assume most people won't. Maybe some others want to talk about video streaming, some others want to talk about more. What I was thinking about was maybe letting this happen automatically. You just go outside and people start talking, and if you want to talk some more, people that give presentations or talking about the same thing, you will automatically aggregate. You can do that. I think that's maybe the most realistic option. So what we have this room. We have, of course, the room outside, and then up the stairs. So the stairs, on top of the stairs to go down to the toilets up the stairs, we also have 2 large meeting rooms that are also reserved for us. So you can move there. There are also some nice seats there if you don't want to sit in the chair the whole time to just do some more discussing or whatever you want. I do think there are a couple of people who will leave earlier. I think Tim and Jeroen. So if you want to talk to them, do that early. There are also a lot of people that stay for dinner, so those can probably wait talking to each other until tonight. I don't know. That's kind of what I had.
Yeah, so I think, I mean, depending on what people are, if you just want to go and check, that's fine as well. If you actually try to organize the groups a little bit, it could be the benefit that people could like put some points on a slide at the end and exchange information and exchange knowledge.
Yeah. That's what I want to do at the end. So at the end, I wanted to like come back for like half an hour and then just talk about what the individual groups talked about and what was interesting maybe to share.
I believe you need to set up groups, dedicated groups if you want that.
Sure. Again, like, what do people want? Do people want dedicated groups or just some loose?
Oh, the lobby is fine.
What's
being there, unorganized is fine.
Okay. Other people? No preference. This is always a difficult part in IT gathering, right? Nobody has an explicit opinion.
Might make it easier because there's flyouts.
Exactly. Exactly. So I suggest that we just go outside, have a small break. I will be coming back here in about 10 minutes, 15 minutes to talk about logging and tooling. I will probably be sitting here alone crying the rest of the but so, make sure you get out of it what you want to get out of it. I think that's the best part. Thank you all for coming, and see you in a couple of hours.
French, Dutch, German.